Hey guys, my name is Shreyas and welcome to Simple Chemistry. In the previous video we talked about the photoelectric effect, but before that we talked about Bohr's atom, and we started to talk about energy levels, and we assumed that electrons orbit the radius kind of like how the planets orbit the sun. Now, I mentioned that this was actually wrong, and that there's more to electrons than that, and that's what we're going to be talking in this video, orbitals. So this is currently the what scientists believe is the true model for the atom as of today, and there's nothing more than this. So this, you can think of this as the final step and what the understanding what the atom truly is. Okay. Bohr's model for the hydrogen atom could only be applied to hydrogen. Scientists began to realize that even Bohr's model of the atom was incorrect. The atom arranges its electrons in a more complex manner than just energy levels. Okay. So what is an orbital? An orbital consists of two electrons and come in four different shapes: s orbitals, p orbitals, d orbitals, and f orbitals. Orbitals can also have orientations. So orientations means the way that they're assigned in space, which you'll be able to see in just a second. Orbitals are essentially just areas around a nucleus where an electron is likely to be found 90% of the time. So instead of electrons orbiting the nucleus, they're just moving in these random paths, and these random paths uh, are calculated using something called Schrodinger's equation, which is way beyond us. But basically, orbitals are just like these regions in space where the electrons are most likely to be found, 90% of the time about, okay? So let's talk about the first type of orbital, s orbitals. So s orbitals can only have one shape and they're spherical, and they look like this, just like a sphere, okay? P orbitals are dumbbell shaped and can have three orientations. So this is what I mean by orientations. So like you can have one, if you look, this is a three-dimensional axis. So this is the x-axis right here, and then this is the y-axis, and then this is the z-axis. So as you can see here on the x-axis, you can have p's of x, which is one type of orbital. You can also have p's of y, a different orientation, and then you can have p's of z. There's three different orientation for p orbitals. And then d orbitals can have five orientations, as you can see here. So you can have d's of x, y. So that means that if you look here, the orbitals are in between the x-axis and the y-axis. If you look at the little shapes, right? Here I have d's of x and z. So like if you look here, the orbitals are between the x-axis and then the z-axis. Here are d's of y, z. The orbital is between the y-axis here, the y-axis, and then the z-axis. D's of x squared minus y squared, which means that the orbitals, instead of being in between the axes, they're right on top of the x and y-axis. And then we also have this interesting looking one called d's of z squared. Okay, so those are the five orientations for d orbitals. Finally, for f orbitals are the most complex orbitals, and they have seven orientations. I don't have a picture of them because you probably don't need to know the how they look in space. Even I don't have them memorized, but you can go and always look that up on Google or in your chemistry textbook and see how those seven orbitals look like. So additional terms to know in orbitals, degenerate orbitals are orbitals which have the same energy. Okay, so we're going to be talking about that more, but just know this term. So whenever you're talking about orbitals which are degenerate, they have the same energy. And nodes are areas where the electrons are typically not found. So let's say we were looking at the p's of these p orbitals, okay? So we can say that, remember again that an orbital is essentially just areas around a nucleus where an electron is going to be found 90% of the time. So if you look at the p orbitals, you can see here that there's a huge bulb here, and there's a huge like region here, but in between that there is just like this dip. So you'd say that you know, you can see like how it cuts in right at the origin of the graph, right? So there you'd say there's a node because the electron will not be found there because there's no shape there. There's just empty space there at the very middle. Same thing here. This might be easier to see here. In the p's of y orbital, you can see there's a lobe here and then there's a lobe here, but in the very middle, it starts to cut in, right? So since it cuts in and the orbital is defined as the area where an electron will be, and there is this is like this region that's just cutting in like this. So you'd say that's just a node because there's no there's the orbital is just not defined there. Okay, same thing of p's of z. You can see that it kind of cuts in at the origin of the axis, and there are in that region the electron will not be found. Same thing with d's of xz in at the origin again, as well as in between the lobes. You can see here like there's one lobe here and there's one lobe here. In between that there's this empty space. That empty space can be considered a node. Same thing with d's of xz at the origin. Everything seems to cut in, and also the empty space between each lobe. So you get the idea. So basically, wherever there's empty space are areas where electrons are just typically not found. Okay. And you wouldn't say empty space as in like over here, like the electron will not be found. We're typically talking about within the orbital where we see regions where there are space, okay? Where there is space. Okay, so that's everything you have to know about orbitals for now. In the next video, we're going to be looking at electron configuration and see how these orbitals come together, and actually look at examples of atoms and start to place all the electrons within the orbitals. Okay, but that's it for now. Orbitals are as simple as that.